Hi, we're here to talk about motion goal 8. You can see what the goal is. We've talked about position time and velocity time graphs. Now we're going to attach an acceleration time graph and look at how all three graphs can show you the motion of the same object. Now they show you slightly different things. So we take a look. We're going to review what we talked about before, which is that we can use a position time graph and a velocity time graph to help us either estimate or calculate the displacement of an object, the velocity of an object, or the acceleration of an object during a specific time. Well, displacement is the change in position. So finding the displacement on a position time graph just means reading where it starts, reading where it ends, and subtracting the two positions. On a velocity time graph, it's more complicated. We have to actually find the area between the time axis and the graph line. We can either use formula or the formulas for triangles, squares, rectangles, whatever it is we need to do to find that area, and that will tell us our displacement during that time. If we're below the time axis, then it will be a negative displacement. Now, velocity, remember, is the change in position over change in time, and that's just the slope of the line on the graph at a given time. The graph that's on the bottom left is a position time graph, and its slope, if I pulled 2 points off of it and found the change in position, the change in the y-axis, over the change in time, change in the x-axis, I could figure out what the velocity is. That's the definition. Now, velocity on a velocity time graph is pretty easy to read. All you do is find the given time that you want to read from, and you read what the velocity is. Now you'll notice that the slope of the line on the graph at the bottom left doesn't change very much, but the so the velocity seems to be constant. If we look at the points on the graph at given times, it doesn't matter which time we choose on the velocity time graph, we're going to get the exact same value. So that works. Now for acceleration, the sign can be determined by the direction of curve. If it curves so that the slope becomes more positive, then it must be a positive acceleration. If it slopes so that the curve becomes more negative, that must be a negative acceleration. If it doesn't slope at all, there must be no acceleration. In the graph on the bottom left, the position time graph there's no curve at all. So its acceleration must be zero. Must be going the same number of meters every second. For a velocity graph, we just look at the slope of the line on the graph. So if you look at the velocity time graph on the bottom right-hand corner, you can see that its slope is not changing at all. Our speedometer is giving us the same reading the whole time, so our velocity must be the same the whole time. There's no acceleration there also. Now we're going to look at acceleration in graphs. You can see that we have a positive acceleration, a negative acceleration, and a zero acceleration graph the whole time. It's actually very normal for you to have not constant positive or constant negative or constant zero, but those are the easiest cases to look at. We're going to limit it to that. We said earlier that the velocity was the slope of the position time graph. It's the change in position over change in time. Acceleration is the slope of a velocity time graph. Acceleration is the change in velocity per unit of time. So the slope of that line tells us what the tells what the acceleration is. If the velocity becomes more negative, the acceleration is negative. If the velocity becomes more positive, the acceleration is positive. Now that means different things depending on which direction you're going at the start. And just like in the graphs on the last slide, if there's no change in velocity, there's no acceleration. We're going to look at the relationship between acceleration time, velocity time, and position time graphs for a few specific cases. We're going to start with the case of no acceleration. If there's no acceleration, then we're going to have a horizontal velocity time graph. And if we have a horizontal velocity time graph, then we're going to have, it says upward slope, but it should just be sloped position time graph. A single slope the whole time. For example, you can see the red line I drew showed 0 acceleration. Now I couldn't tell this from the 0 acceleration, but my velocity is positive. I'm going to keep the same velocity the whole time, which means my slope on my position graph will be constant. It will just head up. I'll go the same number of meters every second regardless. Those are examples of the relationship between the graphs when there's no acceleration. If there were no acceleration and a negative velocity, the velocity time graph would have a horizontal line that went below the time axis, and my position time graph would have a line that, instead of going from bottom left to top right, would go from top left to bottom right. It'd be the opposite direction. Next, we're going to look at an example of positive acceleration. If you have a positive acceleration, then your velocity time graph is going to be upward sloped. Your velocity is going to be more positive at the end than it was at the beginning. And because of that, you'll go a different number of meters every second. That makes your position time graph curved. If we start with a negative velocity, well, making the number more positive means you're going to get closer to 0. You're going to slow down. If we start with a positive velocity, well, making the number more positive means you're going to have a greater speed. You're going to speed up. And that's the example I'm going to show down here. All three of these things show the same motion. We have a positive acceleration. And then we said it's a positive velocity to start with. So if I start from, looks like close to 0, I'm going to get a higher and higher positive velocity. You can see that my upward slope is positive for velocity time graph, which means my acceleration is positive. Now for position time graph, we're going to go faster and faster speed the whole time. So as I look at the beginning slope, it's a little higher than horizontal, but not a lot. But as I go further in time, further to the right on the graph, my slope gets greater and greater, showing a greater velocity. Obviously, my last example, negative acceleration. If we have a negative acceleration, our velocity time graph will be sloped downward, because over time, the number for our velocity, what's on our speedometer, will get more and more negative. And since my speed is going to change, I'm going to end up with a curved position time graph. If I started at a negative velocity, then making the velocity more negative means that I'm going to speed up. I'm going to go from -5 miles per hour to -50 miles per hour. I went faster, and my number got more negative. If I started with a positive velocity, I have no choice but to slow down. I'm going to start with a positive number. That number is going to get smaller. I'm going to get closer and closer to a stop. You can see that's the example we're going to look at here. I drew a negative horizontal line for acceleration. If I start with a positive velocity, like you can see here, my positive velocity starts there, but it gets more and more negative over time. That's going to make it closer to 0, get closer to a stop. My position time graph bears that out. Notice it starts with an upward slope. The line close to the beginning of time in the picture shows you a somewhat diagonal line. That shows us that there's a velocity that's positive. And notice the line gets more and more, well, I should say less and less positive. So it's getting closer to a negative number. That means that the slope is getting more and more horizontal. We'll look at an example of an object, the rolling ball. It's about 1/2 meter down. It's a bowling ball at the top. At 0 seconds, it's gone 0 meters, just like it should. I give a second. After a second, it goes 2/100ths of a meter, 2 centimeters. Not very far. Let's see, but from 1 second to 2 seconds, if it moves at a constant speed, it should just go down 0.2 more, and then 0.2 more the next second after that. But it won't. It went further. After 2 seconds, it went 0.08 meters. So it went 0.6 meters from 1 to 2 seconds, more than it did from 0 to 1 second. Let's see what happens next. It jumps further along the way it's supposed to. So it went another second, but this time it went 0.1 seconds from 2 to 3 seconds, which is further than it went any other second the entire time. We go up for another second. Ooh, it goes even further. So we got 4 seconds, and this time it's going to be 0.32 seconds. That's even further between, I know every 1 second interval it went further. Then we go another second. Oh, a jump way further. One more second, we're at 0.5 meters. Notice the first second we only went 2 centimeters. The last second we went 18. We must be going faster and faster the whole time. Our position time graph is going to prove that that's true. I start out at time equals 0, position equals 0, as we saw in our graph. After a second, it goes 0.2 meters. After an additional second, and this one's a little bit off, it's at 0.8 meters. Another second, it's at 0.18 meters. 4 seconds is going to give us 0.32 meters. And 5 seconds is going to give us 5 meters. You can see that every second you're going further and further up the graph. And if you make a curve of it, or you make a line through it, it makes a nice upward curve. The slope gets steeper and steeper over time. What that means is that our velocity is not staying constant. We're not going to draw a graph of it. Not going to, plot the numbers for it. Though you're smart, you probably could. If we take 1 second though, or we know that when we went back in our graph, it started with a positive velocity. So we know that it's going to start, a little bit positive, close to 0. We also know that the slope gets more and more upward, more and more positive. So if we draw a line to represent this, it's going to be an upward line, diagonal. It's not going to keep the same velocity the whole time, but it is going to be positive the whole time. It's getting more and more upwardly steep. You can see that although the line's getting more and more velocity, we're still getting this. The change in velocity per unit of time is not changing very much. We've got a constant speed or a constant slope here. That leads the acceleration to be positive. I hope that example helped. Make sure you go through all the other examples and present those to your teacher when you're done. Thanks for listening and watching.